So I'm so glad you asked about valence electrons, because that's what I want to talk about next. So, what are valence electrons? The valence electrons are the electrons on the outside of the atom. They're the ones in the highest energy orbitals, highest energy levels. And they're significant because being on the outside of the atom, those are the electrons that interact with other atoms. And the interaction with other atoms is what causes chemical properties to be what they are. So the valence electrons are very important. For main group elements, it's very easy to tell how many valence electrons an atom has because it's equal to the group number. And these are the 1A, 2A, 3A group numbers as opposed to the 1 through 18 group numbers. But if we look at nitrogen, nitrogen is in group 5A. It has 5 valence electrons. If you look at the IUPAC numbering, it's in group 15. We'll just cover up the 1. It's got 5 valence electrons. It still kind of works. So the group number corresponds to the number of valence electrons. All the other electrons are called core electrons because those are in the core. They're more on the inside. And they don't really do anything in chemical reactions. They're just there. So now we can begin to understand this periodic law and why these properties recur. So here we have just the first 3 periods of the periodic table. And you might say, well, why is helium over here? Why isn't it over there? Wouldn't that make more sense? Well, in some ways it would, right? So if we stuck helium here, and helium has, well, let's get rid of that. Let's write it up here. This would be 1s2, and that matches up real nice with these other ones, right? Well, hydrogen and helium are both little brothers in the element family, and so they break lots of the rules. The reason that helium is over here is because helium has a full valence shell, and so behaves like these larger ones that have full valence shells, and we'll see a little bit more about that later. Group 1A, we've got 1 valence electron. Group 2A, disregarding him. Well, he has 2 valence electrons too, but these have 2 valence electrons. Boron, 3, 4, 5, 6, 7, and these guys have 8 valence electrons, except for helium, who only has 2 electrons. These guys, they just mess up everything. The reason that oxygen and sulfur have similar chemical properties is because they have the same number of valence electrons. Okay, so write an electron configuration for phosphorus, identify the valence electrons and the core electrons. So phosphorus, 15 electrons. You want to do an orbital diagram first, or you want to go straight to the electron configuration? Orbital diagram. So phosphorus, 15 electrons. So we're going to need minimum of 8 beds, right? So let's just start drawing rooms. Bless you. 1s. Bless you again. 2s. There you go. Bless you all day. 2p. 3s. And if we're going to get into that 3p room, we have to draw all 3 beds. So that should be plenty of beds for these electrons. Let's see where they're going to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Turns out we did need all the beds. How many unpaired electrons are here? 3 unpaired electrons. Okay, so now let's do the electron configuration, because that's what it's really asking. 1s2, 2s2, 2p6, 3s2, and then 3p, how many? 3. So the valence electrons, you look at the hotel, what's the highest floor that has any electrons staying on it? The third floor, right? That's not what I wanted. So here's the third floor. The third floor has electrons on it. Those are the valence electrons. They're the highest level. So these are the valence electrons. I often call them VE, valence electrons. And then the rest of them are core electrons. So these guys are the core electrons. Not cove, core. Yes?
So when we get to where the levels fill up in a different order, it's still the highest number.
Yes. Yeah, so if we had 3D and we had 4S and 4P and things get all wonky, we're still looking at the highest principal level. So we're looking at the biggest number here, the highest floor in the hotel.
And it's the whole floor.
And it's all of them, yeah. So we'll see that you could have, well, let's just draw that over here, dot, 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 and you could have 4S2, 3D10, 4P2. Well, what's the highest floor? What's the highest energy level? It's the fourth one. So you're going to count all the electrons on the fourth floor. So that would be 2 here and 2 there. These don't count because even though their room is more expensive than this one, it's not on the highest floor. And that's what the valence electrons are, the highest principal number. Yeah. That's a good question. So argon fills up the 3p and that makes it a noble gas. And so, potassium just has one more electron. Why isn't it like that as well? Because it's got one extra electron. Oh, like calcium that fills up 4s, that's filling something up. There's something magic about the number 8. When we have S and P full, that's when we get a noble gas. It's the 8 valence electrons. 8 valence electrons is kind of magic. We'll just leave it magical at this point. Any other questions?
In the book, it talks about, I forget the name of the scientist, but he tried to relate chemistry and music and organize the periodic table by octaves. Is that why? Because they knew things about the number 8?
Well, I think it's an interesting, I don't know if it's a coincidence or not, but that the periods, at least at the beginning, are 8 elements long, and on a piano keyboard, we have 8 keys in an octave. I don't know how much the octave influenced his thought process, but he did notice this, that, oh, look, there's this correlation here. Maybe there's something to this. And some of those early research ideas are really interesting to look at. Okay, so now I'm going to show you how you can find all this stuff on the periodic table. So we can divide the periodic table into 4 blocks that represent the different quantum sublevels. The group number tells us how many valence electrons that atom has, and the row number, the period number, gives us the highest principal quantum number for that element. Ta-da! So again, we might want to imagine helium being over here, because he kind of belongs over there. but he really belongs over here more. So that first row, we just have to yeah. The second row, then things really become much nicer. But so this block here, and we can recognize this as the block because it sticks up, right? If we're going to try to make, if we were going to try to select this, like in an Excel or something, we could select all of those at once, right? That's one block. And then we could select all of these at once. They're not squares, but they are rectangles, right? And then there's this one down here. And that's why, helium just being a butt and sticking out over there. Okay, so this is the S block. How many electrons can be in an S sublevel? How many people in an S room? 2. There's 2 columns. This is the P block. How many people in a P room? 6. It's got 3 beds. You can put 6 people. 1, 2, 3, 4, 5, 6. Guess how many columns there are here? 10. And down here? 14. 7 times 2. The period number here corresponds to the floor of the hotel, the principal quantum number. So this is principal quantum number 1, 2, 3, 4, etc. So this is 1s, and this is 2s, and this is 3s. Over here, this would be 2p. Notice there is no 1p, right? And this would be 3p. Now, the D's, this is where it gets a tiny bit messy, because is this 4D? No. The order got messed up, right? So this is how I think about it. I think of, well, it was originally up there, but it sank, right? Have you heard that the floor of the valley is sinking because we're pumping water out of the aquifer and the ground is actually sinking? We're getting lower. Not, we don't notice it, but it's measurable, right? So that's what happened here. They pumped out too much groundwater and that whole block sank. I don't know, whatever helps you remember. So when we're looking at these guys, for the D's, we look at n minus 1. What's n? N is that principal number that's over here, is the period number. N equals 1, n equals 2, n equals 3, etc. So here for these guys, they're in the 4th row. Subtract 1. So this is 3D. This part didn't sink. That's, this is the mountains. This is the Sierra Nevadas, and that's the coastal range. Then we're back to 4P, and here's 5S, and then these guys are sunken, right? So this isn't 5D, this is 4D. 4D back to 5P, 6S, and this would be 5D, but then there's this little gap here, and the numbers don't quite work out. 57 to 72, what? Well, because this piece should be in here. Now the one we have on our wall, because of the geometry of our space, is set up the way it should be. We actually took a knife and cut up the periodic table and stuck it back together, and we see that those guys are actually in here, right? Right in here. So those sank more, right? So down here, for the F block, we have n minus 2. So from lanthanum, we come down here to cerium. So that should be in row 6, and so this 6 minus 2, this is 4F. 4F, and we're back here, this is 5D, 6P, 7S, 5F, 6D, 7P. That's the filling order.
So the rings are only, the F blocks are only level 5 and 6. Sorry?
Well, the F block starts in
4.
4.
Sorry, 4 and 5.
Yeah, 4 and 5. And this, we expect that this pattern would continue, but all of these guys down here are man-made elements, and it's really cool that they've been able to make them, but they can't make enough to even get an accurate mass. They're really unstable. They don't know what color they are, so can we study their electron structure? Not really. Are there things that could be made past that? Probably, and I'm sure there are several research groups trying to do that right now. But we're not going to worry about it. Yeah.
Why are there some of these, but not the whole thing? Is it just because they're going to have to run through?
What do you mean, like that this one, the D first and then here?
Yeah, the bottom one. They're like.
Why does it stop here?
No,
The green.
There's like.
Oh.
First one there's E. And then
Yeah,
there's
so
E.
that's where things get very irregular,
Oh.
and we're not going to worry about them. We're going to talk about irregular electron configurations, and I'm going to tell you 2 that you need to be aware of and show you why they might be doing that, but we're not going to worry about them. So this one, is 6s2, 4f1, 5d1. Well, why isn't it 6s2, 5d2, or 4f2? Why did they split up, right? That gets complicated, and we're not going to worry about it. Okay, so we can write electron configurations from the periodic table. So if we're going to look at chlorine, and we're going to do the noble gas configuration, we find chlorine on the periodic table, and then to do the noble gas configuration, we're going to go up a row and to the end to find out what is the previous noble gas. So here it's neon, and so we write neon in brackets. And then we write down what's happening after that. So we've covered up to here, and now we're going to look at the third row. So this is 3s2. So we're filling that up. So we're going to write that down. And then we jump across this space and we come over here. And this is 3p, and we're going 5 blocks over. 3p5.
So when you're writing that, Irregular, we wouldn't say, like, this is chlorine. We would just say that because it shows that it's chlorine. We would like say chlorine.
Well,
Or, I mean, there's not like a right way to.
like if I'm doing a bunch of these, I'll probably specify, I'll indicate chlorine and then show its electron configuration. Yes?
So should we always use the gases?
No, we shouldn't always use the noble gas. I would recommend doing it whenever you can, because there's fewer things to write down, so fewer possible mistakes, right? With all the P's and S's and 3's and 6's and stuff, you can get stuff written down incorrectly. You need to be able to do it both ways. This stuff will be multiple choice on the exam. And so if I ask you for the electron configuration for chlorine, I might give you just all noble gas configurations. And one of them will be correct and the others will be wrong in some way. Or I might give you full electron configurations, again, one being correct and the others being screwed up in one way or another. And you have to pick the correct one. So you need to be able to do it both ways. So let's do this the other way. Let's do it from the beginning. And let's do a different color here. I don't know, maybe red. No, purple. We'll do purple. So if I'm starting at the beginning, I'm just going to start in the upper left corner of the periodic table. And this is 1s, and it kind of goes over there. So 1s2, and then I'm going to come across here. That's filling up the 2s, so 2s2. And here we go, 2p all the way across, or 6. This is the 2p block, and I'm going 1, 2, 3, 4, 5, 6 blocks in there, all 6 of them. And then across here, 3s2. And across here, I'm going 5 blocks in, 3p5. Yeah, so this is the electron configuration of neon. And so I can use neon in brackets as a representation of that instead of writing all the stuff out. With these smaller ones, it's not such a big deal. You know, you get down to like tellurium or something with 52 electrons, and then it gets really tedious, right? So here's a regular periodic table. Determine the electron configuration of bismuth. Well, where's bismuth? Right down here. Now we could do the whole thing. We'll do the whole thing and we'll do the abbreviation. We'll do the abbreviation first. So what's the previous noble gas? Xenon. We're going just up to the next row and all the way to the end. What that element is? Xenon. And so we're going to write that in brackets, so that's xenon. And then we're going to fill in what comes after. So after xenon, we're coming through here. That's row 6, the S block. That one's fine. We don't have to mess around with it. So that's 6s2. And then there's 1d here, and then we're going to get into all of these F's, and then we're going to get back to D. We can't have 2 entries for the same sublevel. And so instead of writing that there's 1d electron here and then a whole bunch of F's and then the rest D's, we're going to lump all the D's together. They're going to show up after. So we're going to say, well, you just scoot over and get with those guys, and we're going to come down here. Mm-hmm.
I'm trying to understand the whole like shifted down.
Uh-huh.
So would that apply? Would it actually be the 7?
Well, this is in the 6th row, but it sank. It was originally supposed to be up here at the 4th.
Okay.
So this is, well, that's not what I meant to have. This is where the D's would be, but they sank. And then the F's should be up here, but they sank. They sank down further, right? So the edges of the valley floor sank and the middle sank more. I don't know. But what we should remember is for this D block, we're looking at n-1. And for the F block, we're looking at n-2. N is the period number. So this is in period 6. So 6 minus 2 is 4. So this is 4F all the way across. So I'm going to write 4F14. And then I'm going to go back and pick up with the D's where I left off. The D's, we're going across, there's 10 of them. Those are n-1. They are also in row 6. But 6 minus 1 is 5. So this is 5D, 10. And then we're over here. The P block didn't sink, so that's 6P. And we're the third block in, 6P3. Any questions? It kind of does matter if the F's are first or the D's go first. That's not something I'll try to trick you on. But we show these in order of energy. And so, yeah, that 1D would fill before the F, but as you can see down here, things are really wonky. And so we're just going to go with in general. So in general, the 4F is lower in energy than the 5D. And we don't want this to get real complicated. We don't want to have 5F1, 4F14, 5D9. You know, we need it together. Okay, so let's do the regular, the whole thing. So well, I guess I have to do that too. I should have just erased the whole thing. Maybe green. Okay, so here's bismuth. So I'm just going to start at the top, right? There's 1s, that's all weird. I'm not going to have enough room, but I'll just start over here anyway. 1s2, 2s2. Over here, 2p6, 3s2, 3p6, 4s2, and then I'm into this D block. So this is D10, but it's not 4D10, it's 3D10. And then this is back to 4, 4p6, 5s2, the D's again, not 5, it's 4, 4d10, five p6, 6s2, six minus 2 is 4, that's 4f, 14, and those D's in there, that's 5d, 10, 6p3. The order of filling is in the periodic table. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p.
Is that just a coincidence of the periodic, the table organized in a way that, like, organized intentionally?
Is that a coincidence, or is it organized so that works? Okay, so it's not a coincidence. It's people observed some properties that caused them to organize things in a particular way, and then later we came up with a theory that explains why it is that way. Now, here's a question, regardless of your religious beliefs. Could this have happened by chance? The periodic table, this organization, random chance. Seems pretty unlikely to me. Personally, I do believe in God, but if you don't believe in God, there's another theory. Now I'm blanking. Intelligent design, right? That there is some being that made it all. Okay, so that's kind of far-fetched too, but that's easier for me to swallow than that this happened by chance. Something to think about. Let's do some more. Write electron configurations for each element. We're going to do chlorine, silicon, strontium, and oxygen. So, chlorine. Chlorine is over here. We'll just do the noble gas ones. Does that sound good? So for chlorine, which noble gas am I going to use? Neon. Because that's the one that's just before it. And then after neon comes 3s2, right? And then 3p5. So these should seem easy after bismuth. I won't do bismuth to you on an exam. Any questions about chlorine? Okay, let's do silicon. Get this out of the way. Well, where's silicon? That's over here. So noble gas, shorthand, we're at neon again. And then after neon, 3s2. And then over here, that's the 3p block, but we're only going 2. Do you see what I'm doing? It's a very nice pattern. Okay, strontium. Strontium is down here. Can't even make a square anymore. Just for practice, let's do the whole thing for strontium. Otherwise, that one ends up so easy. So if we're going to do the whole electron configuration, we start at the beginning, row 1, 1s, 2. We go to the second row, 2s, 2. Then we go over to this block, that's the p block, 2p6, 3s2, 3p6, 4s2, oops. And then what's this part? That's 3d. There's 10. If you don't remember how many, just count the columns. There's 10. And then over here, we're back to p again. That's in the fourth row, so that's 4p. All the way across 6, and then here 5s2. Noble gas shorthand would be easier to be krypton 5s2, but you know, what's the fun in that? And then oxygen. Here's oxygen. You write it down. So what's it going to be? 1s2, 2s2, 2p4. Exactly. Pardon me? Could you use helium?
Yeah.
Yeah, you could.
Even though it's weird.
Yeah, it's kind of weird because does that really save you much? Doesn't. Whoops, not 6. 6 out of habit. 4. Yeah, you could. Any questions? Irregular electron configurations. So because of the sublevel splitting the 4s fills before the 3d. The difference in energy there is not large. It's a small difference. And so some of the transition elements fill that up irregularly. And in the analogy of the hotel, this is like a Groupon deal, where if you meet these specific requirements, you get a benefit, right? A discount. These electron configurations must be found experimentally. And so I'm going to show you some of them, and I'm only going to require you to remember 2 of them. So here are 5 irregular electron configurations. There's more, especially with those guys way at the bottom, but we're not even going to think about them. But these are the 2 I want you to know, chromium and copper. So let's look at the orbital diagram for chromium and see what's happening between the expected and the experimental. So for chromium, we've got argon, and we're just going to look at the valence electrons, well, the ones after argon. So there's 4s, and then there's 3d. So the 3d has 5 orbitals. What we expect is that the s would fill, and then the next 4 electrons would take their own beds in the d room. Right? That's the pattern we've been learning. But that's not what it actually does. You know, to self-put a grid on this so I can draw better. What it actually does is, well, we could think of it this way. This is what we expect. But what actually happens is that this guy comes over here. Does this look more symmetrical and nice than this one? It does. Here I've got the 4s is half full and the 3d is half full. There's a coupon that if you do that, you get a discount. This is lower in energy. Why? Well, there's something special about completely full and half full sublevels. And we don't want to go any farther than that. And it kind of makes sense, you know, it's like, well, if the energy difference here is pretty small, then this guy, you know, maybe it's like $0.25 a night to have your own bed. Even if you're cheap, you're going to do that. It's not like it's $20 or something, right? It's just a little bit, and then there's actually a discount that makes it cheaper. So that's what chromium does. And then let's look at what copper does. Oh, that got kind of fat. So we expect that copper would fill up like that, have 9 electrons in the d orbitals. But what actually happens is that the guy sleeping upside down here in the S room moves over and sleeps upside down in the D room. Well, how's that better? Well, it's more symmetrical, isn't it? Here we have this big subshell that's completely full, and this one is half full. Here we had this little one was full, and this one was not quite full. This is lower in energy. And this is a place where the non-scientific explanation is much easier to deal with in the scientific explanation. Yes?
Or has this been like observed?
This is experimentally determined.
Okay.
Yeah. And so we observe that this happens, and then we try to figure out, well, why? How would it do that? And that led to, looking at how the energy is lower when that happens. And so if we look at molybdenum, it has a similar configuration to chromium, and so it does the same thing as chromium, but just in the upper level. And then things get a little wonky, and so ruthenium 5s2 4d6 becomes 5s1 4d7. It does. And I'm not going to worry about why, because I have more pressing things to think about, like how I'm going to pick up my son from school and get to my daughter's volleyball game, right? That's more important than weird electron configurations. This one makes a little more sense. What happens here is these two electrons both go over here, so then we have an empty level and a completely full level. And so we can look at these on a case-by-case basis and kind of figure out, well, this is maybe why it would do that, but the only two you need to know are chromium and copper, and I think those make the most sense. Any questions? I can almost guarantee you I will try to get you with the irregular electron configuration of chromium or copper on the exam. So then it's not a trick because I told you I was going to do it. Yeah. Chromium and copper. Mm-hmm. So if I asked you what the electron configuration for chromium is, I would probably give you this one, the expected, and the one that's found experimentally, and you would have to choose the experimental one because that's the correct one. Because I told you it was, and I told you to remember it.